Today we're going to talk about approximations for integration, something that you've done in the past, right? You guys did left-handed and right-handed approximations in Calc 1, right? And if you had me for Calc 1, I also taught you the midpoint, which is one of the topics for today. And I discussed the trapezoidal with my Calc 1 group. For those of you who didn't have me for Calc 1, I'm going to talk about them just so you guys can see. I'll do just some quick sketches for you guys to try and remember, and then I'll actually use the rules that we have to go ahead and build these problems. So with the midpoint, what's going to happen is if you have something like this, right? And we close it off at this point, so we'll call this B, and this here A is the orientation. In fact, let me get better than that. Let me say that this is A so we can see it. Okay, so in the midpoint, if we were going to do two approximations to this thing, we'd have to break this thing up into two pieces, right? Two chunks. So the ends are obviously going to be hard endpoints, right, for whatever it is. And then if I broke it up into two, right, if I had two approximations, so my n in this case would be 2, those would be the widths of the rectangles that I'm going to build. With the midpoint, though, what ends up happening is this. I'm going to take the middle point, and that's where I'm going to create my rectangles for my approximations. So in between the two sections, I'm going to find my midpoint. That will be the height of my rectangle, and then I would add up those two to be able to approximate the area under the curve. Does that make sense?
Yes.
Okay. The difference between that and the trapezoidal is in the trapezoidal, and again, I'm basing this off of Calc 1 with you doing left and right-handed approximations and remembering that. If I take that same curve and I take that same A and that same B, right, closing it up, and if I'm going to do 2 again, now what ends up happening is this. I'm going to use a trapezoid. So now I'm going to go from this point to this point with a straight line. And then from this point to this point with a straight line. And that's going to now become my 2 trapezoids for this. Does that make sense?
Yes.
So that's the difference between the two. What we ended up finding is left hand, right hand, midpoint. Trapezoid was even better than midpoint. And then today we're going to add a fifth one, which is the Simpsons Rule. And Simpson no longer goes with straight line functions. So it's no longer trapezoid, it's no longer rectangle. It's now going to be parabolas. And we'll go from there and fix that, okay? But these are the two. Midpoint, you're going to take the width, find the middle value, the middle x, and then plug that into the function to find your height. Trapezoid, you're going to take the two ends and create a trapezoid and be able to solve it that way. These are the two equations that you'll use for midpoint and trapezoidal. So let me show you an example so we can go ahead and solve these problems, okay? All right. So in this first example, I'm going to try to find out what the trapezoidal rule, I'll do that one first, and then the midpoint rule tells me when I have an n of 5, to approximate this integral, okay? So one of the things that's important that we need to remember from finding the left and right-handed approximations is we need to remember how to find delta x. And so delta x, we should remember, was b minus a over n. And in this case, my b is 2, my a is 1, and my n is 5. So my delta x in this case is going to be 1/5. Is there any questions about how I get my delta x? All right, cool. You guys remember some stuff. Okay, so with the trapezoidal rule, one of the things that's important is we notice that this trapezoid, right, this middle line is counted how many times when I add up these two trapezoids? It's counted twice. It's counted twice because it's this. Remember it's 1/2 base times 1/2 base 1 plus base 2 divided by times the height. So here this is going to be counted twice, and so that's why we have these 2's inside of the trapezoid. Okay, so when I go to do the approximation of this from integral from 1 to 2 of 1 over x dx, and I'm going to do it for a trapezoid with an n of 5, I'm going to get 1/5 over 2, right? Because the formula tells me it's the delta x over 2 right here, correct? Then I'm going to go f of 1 because that's my left endpoint. My delta x is 1/5 or 0.2, correct? So my next point is going to be 2 times f of 1.2 plus 2 times f of 1.4 plus 2 times f of 1.6 plus 2 times f of 1.8, and then I'll just do this one down here, f of 2. Right? Because that's the endpoint on the far side. So when we go to do this, 1/5 divided by 2 is the same as 1/10. 1/10 is the same as 0.1. So f of 1, remember we're plugging into the function, and so we're plugging into the 1 over x. So that's going to be 1 over 1 plus 1 over 1.2, let's not forget times 2, plus 2 times 1 over 1.4 plus 2 times 1 over 1.6 plus 2 times 1 over 1.8 plus 2 times 1 over 2. Are you guys recalling this kind of stuff?
Yeah.
So then from here, finding each of the values, you can use your calculator, that's fine. Well, let's do it. I'll get my calculator and do it. So I'm going to get 0.1 times 1 plus 2 divided by 1.2 is 1.66667 plus 2 divided by 1.4, 1.42857. Obviously there's going to be more numbers to this, but that's okay. 1.25, 2 divided by 1.8 is 1.11111 forever, and then 2 divided by 2 is 1. Close that bracket. And this ends up being, or having an approximation, and remember, these are approximations, they're not exact. And that's the whole point of what I'm teaching you guys today. Since they're not exact, what does that tell me? What do you guys think I'm alluding to? That's not it. Not crickets. I'm alluding to error. There's going to be some error. And so now we're going to analyze error with these problems once we get through it. Okay, the reason I'm showing trapezoid a little bit more is because, well, it's probably the one that's going to be a little bit more confusing with the 2's. Now, when I go to do the approximation for midpoint, it's 1 over x dx. I'm going to go m of 5. And the formula tells me it's 1 over delta x, right? So we can see from the midpoint, or I'm sorry, it's delta x. Delta x times these values, and each of these are means. So I'm going to go, okay, m of 5. The delta x was 1/5. And then since we're doing 5 increments, I want to show you guys how to be able to find this. Since it's 0.2, right, is 1/5, what's between 1 and 1.2? What's right in the middle between 1 and 1.2? Or what is the average between 1 and 1.2?
1.1.
That's right. So this first one's going to be f of 1.1 plus, and now we could find the mean every single time, but instead of having to do the mean every single time, we know what we're going to be adding each time is the delta x shift. And the delta x shift was 1/5 or 0.2. So I could just add 0.2 each time. So the next one should be 1.3. But if you're unsure, just think of it this way. The next slice would be from 1.2 to 1.4. And what's the average between those? 1.3. Are you guys getting that, or do I need to draw a picture so you can kind of see what I'm talking about?
Can I see a picture, please?
Sure. So just real quick. So if we're looking at something like this, right, because we're only looking at it on this side from 1 to 2, right? And we're saying that each thing, that's going to be 1.2. This one's going to be 1.4. Here's 1.6. Here's 1.8. In fact, I'm going to shift over so I have more space. 1.1, 1.2, 1.6, 1.8. Now, halfway between them, and I'll do it in a different color, halfway between this is 1.1. Halfway between these guys is 1.3. Halfway between these is 1.5, 1.7, and 1.9. Does that make sense? So that's where I would make these rectangles. I should do that in a different color.
Yeah, that makes sense. Thank you.
Okay. So that's just there for you guys to be able to see. That's how I'm getting my midpoints, right? Because the delta x is 0.2 each time, right? 1 over 5 is 0.2. So my increments are going to be 1 over 5 increments, which should give me 5 different cross sections. 1, 2, 3, 4, and 5, just like the n that I had mentioned, right?
Right.
Okay. Cool. All right, can I erase this picture?
Yes.
All right. Thank you. I need the space. Okay, so then the next one should be f of 1.5 plus f of 1.7 plus f of 1.9. And we're never going to get to the end because it's midpoint, right? And then the approximation of this, you guys can do it with your calculator. I'll write it down, at least this piece. 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. and that should approximate to be 0.691908, right? Not bad. The actual value of this, if we were to do the integral, which you guys can all do now, that's going to be ln of x evaluated from 1 to 2, which is ln of 2 minus ln of 1, which just gives me ln of 2. And that is, and I only went 6 decimal places, but which one's more accurate? We could do it. Here, I'll do it. 0.693147 minus 0.695635. That's not bad. 0.693147 minus 0.691908. Oops, go back. Let's see what did I do wrong. That should be 0. Deleted my work. Took a bump. And actually, what's funny is midpoint is more accurate in this case, which is cool. As we get more and more approximations, trapezoid should typically be better, but in this case, the midpoint was actually better. And all I did was subtract the actual minus the approximation to see which one was closer. Does that make sense?
Yes.
Okay. Now we need to talk about how we can find error. And this is going to be our error-bound formula. So see that this one is E of t, error of t, and error of m. So this one is for the trapezoid, and this one is for the midpoint. And these notes are already up too, so if you guys wanted to just print them out, you can. And now what I'm going to do is I want to find out how large should we take our n in order to guarantee a specific accuracy. Okay, so in mathematics, we want to be accurate, right? And so in order to do that, we've come up with formulas to be able to determine accuracy. Okay, so in this problem, one of the things that we need to note is look at what's happening here. To find our k is going to be less than or equal to the absolute value of what? What do you guys see that to be?
The 2 times derivative of the function.
The second derivative, right?
It's second derivative. There you go, sorry.
Yeah, it's the second derivative. So that now means that we need to be able to take the derivative of our function. So it's important when we go to attack these problems with the trapezoidal and midpoint rule to be able to take the derivative. So if my function I know is 1 over x, right? The first derivative of this function should be a negative 1 over x squared, right? Does anyone need me to show how that is 1 over x squared, a negative 1 over x squared?
Yes, please.
Okay, no problem. So the way I'm going to do it is I'm going to go x to the negative 1, and then when I take the derivative of this, I'm going to use power rule. So I'm going to get negative 1 x to the negative 1 minus 1, which is going to give me negative 1 x to the negative 2, and that becomes negative 1 over x squared. Does that make sense, Miranda?
Yeah.
Okay. Then the next derivative is going to be 2 over x to the third. Do you guys need me to show that one?
No.
It's okay if someone does, I don't mind. But again, it would be the power rule. All right, let me erase this. Now that I have that, what I'm going to do is I'm going to go see if I can find what my k is, okay, for this problem. So I'm going to go, okay, the derivative, the second derivative of x, right, the absolute value of the derivative of x, is going to be equal to 2 over x to the third. Agreed?
Agreed.
Okay. And then what that's going to do for me is it's going to be less than or equal to 2 over 1 to the third. And so my k is going to be 2.
I think someone in the chat asked to see the second derivative. How to do it.
Oh, okay. So second derivative would be negative x to the negative 2. So it's a negative 1 times a negative 2, x to the negative 2 minus 1, which is going to give me 2 to the x to the negative 3, which is 2 over x to the third. Thank you for speaking up, Brian.
No problem.
Does everyone get how I got this value?
Yes.
Okay. So may I erase that derivative now?
Yes.
Okay. So this is my k. So now I know k is 2, a is 1, b is 2, right? Because a is my lower bound, b is my upper bound, and I just found k. So now, since I'm going after the trapezoid approximation first, I'm going to use this. Okay? And so I'm going to go 2 minus 1 cubed over 12n squared, but I want it to be less than that accuracy that I asked for. Are we okay with that?
Yes.
Yes.
Okay. All of that stems from just substituting into here, right?
Right. Yes.
Oh, by the way, my computers are coming tomorrow, so we should be good to go going forward without glitches and stuff. So I'm happy about that. All right, so in the manipulation of this, I'm going to get 2 over 12 n squared is going to be less than 0.001, or it's asking for an accuracy of the 10,000th place, which is pretty dang good. So I'm going to get 2 over 12 times 0.0001 should be less than my n squared. So n will be something, this restriction should be something that is 1 over the root of 0.0006. And so that's going to give me 40.8 for an n, but my n must be an integer, so therefore n should equal 41. I didn't round up because of it being a 0.8. If it would have been 40.1, I would have had to have gone to 41. Do you guys understand why?
I don't, Professor. Can you explain that for me, please?
Yeah. So the reason why is because if it takes 40.1 n's to be able to get to the right accuracy, 40 would not get us to have the accuracy that we need. So that means we have to go beyond it to be able to get the accuracy, since we're talking about integers. Does that make sense?
Yes. Thank you.
So it's all about that. It's the accuracy. So if you get 40.001, you have to go to 41 because it's bigger than 40. Clear?
Clear.
Okay.
Yeah.
Okay, good. That's critical. All right. We just did it for, that was for trapezoid. So you guys know. And I should put that here so you guys know that's for trapezoid. Now I'm going to do it for midpoint. Okay? And look at the midpoint. It's going to be kb minus a cubed, but now instead of 12, it's 24. So the difference is the 24. My k is going to be the same, so my k is still 2. My a is still 1. My b is still 2. So I'm going to get 2 minus 1 cubed over 24n squared. That's got to be less than the accuracy that we want. And so I'm going to get 2 over 24 times 0.001 should be less than that n squared. So n is going to be 1 over the root of 0.0012. And that's going to give me, let me do that on my calculator, 1 divided by that root. Do you guys see why I want you guys having your TIs with you?
Yeah.
So if that's my n, what should my actual n be?
29.
It's got to be 29. So that means I would have to have 29 divisions from 0 to 20, from 1 to 2 to be able to get an accuracy of to the 10,000th place. Imagine if you had to do that by hand. That would suck. But we can. We don't want to, but we definitely can. Are there any questions on finding error for midpoint or trapezoidal rules?
No.
All right, good. All right, can I go on to the next thing?
Yeah.
All right. So now we're going to play with Simpson's Rule. Where did you get Ka values? Oh, okay. So let me go back up here because it was from the get-go. So, no, don't worry about it, Aaron. It's cool. It's better to ask and know. It's recording, so if someone would have missed it, it's good for them to see that this is something that's important. My A is going to be the lower bound. My B is the upper bound. And my K comes from this right here. It's the absolute value of the second derivative has to be less than or equal to. So when I took the second derivative, that's why I took the second derivative. And what I did is I plugged in the derivative, and then what I substituted in was the 1, and the reason I used 1 was it was the lower bound in this case, which the gap for the whole thing was 1, and so that gave me my K to be 2, and that's how I got K is 2, A is 1, B is 2. Got it? All right, no problem. And you would have seen it from up here too. In the rules, there's your A, there's your B, and then the K was found from here. But, all right, no problem. All right, let's go to Simpson's Rule. Now, what Simpson's Rule does is it no longer takes straight line paths. It tries to create parabolas to get approximations. And so if we're talking about a curve, do you think a curve function is going to give us a better approximation than a straight line.
Yes.
It should, right? It should. So what we end up seeing is the better we can get to getting the curve, the better it's going to be. Although it's kind of funny, these are all approximations. We now know that with integration, if we do an infinite number of straight line functions, we're going to be exact. So, but the development of how we got our calculus is so amazing that these men were coming up with, men and women were coming up with different ways of trying to approximate to get more and more accuracy. So I think it's cool. So, all right. So Simpson's Rule, the one thing that's interesting about Simpson's Rule, and you can look at the explanation for how it's done. I'm not going to go into that because you won't really use these rules much going forward. But there's a pattern that he observed that made these coefficients hold true. It would go 1, 4, 2, 4, 2, 4, 2, 4, and then back to 1. So just like the trapezoid was 1, 2, 2, 2, 2, 2, 2, 2, 1, Simpson, when he looked at these curves, saw that it would alternate in between from 4 to 2, 4 to 2, 4 to 2, which is kind of cool. Okay? But the big difference between Simpson and the others is that Simpson would use parabolas for approximations. Okay? Now, let me go ahead and do this example for you guys so you guys can see this. It should be pretty cool. So what we end up seeing, and the first thing that we should do with this problem is find our delta x. One important thing. This is critical to remember. If you're going to use Simpson's rule, your n must be even. Okay? I'm sure that has something to do with it being a parabola. Parabolas have an even power, but I'm sure somehow, some way that's involved. But remember that n must be even. So let's find the delta x in this problem. So the delta x in this problem is going to be 2 minus 1, right? And that comes from this formula right here. You should remember that from Calc 1, but if not, no big deal. So 2 minus 1, and my n in this case is 10. So I'm going to have 1 over 10, or for simplicity's sake, we'll just use it as a decimal as 0.1. Okay? So we know what this means, delta x being 0.1 means every time I shift over, I'm going to go 0.1 over, right? So I'm going to go from 1 to 1.1, from 1.1 to 1.2, from 1.2 to 1.3, until I get to 2. Does that make sense?
Yes.
Yeah.
Okay, good. Now, since we have these values, we can go ahead and try to do this. So we're going to go the integral from 1 to 2 of 1 over x dx is going to be approximated by using Simpson's rule. That kind of looks like an integral. I should make a better s. S. Okay, and so what that's going to be is it's delta x over 3. So my delta x is 0.1 over 3. And then I'm going to go f of, my initial is 1, right? Plus my next increment is going to be 1.1, 1.2. Oops, what did I forget?
4.
Yes.
The coefficients.
The coefficients. The coefficients. Don't forget the coefficients. So it should be 4 times f of 1.1 plus 2f of 1.2. And you guys get the pattern, right? So then it's going to be Or do you want me to write them all down? It's okay if you want me to.
No, you said it's up to 2, right?
Yeah, it goes 4, 2, 4, 2, 4, 2, 4, 2. So f of 3 would be 4, f of 4 would be 2, f of 5 would be 4, f of 6 would be 2, f of 7 would be 4. So then f of 8 would be 2. Then 4 for f of 1.9, and then f of 2. Do you guys see how I got that?
Yes.
And it's kind of a giveaway, to be honest. The last two are always going to go 2, 4, 1. How this goes 1, 4, 2, this will go 2, 4, 1. Well, depending on the number of ends, right? But okay. All right, so then from here, I'm going to get, what is that? Should be in the calculator. Zero 0.03333, whatever, of 1 over 1 plus 4 over 1.1 plus 2 over 1.2 plus that should be 4 over 1.3 dot 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 2 over 1.8 4 over 1.9 plus 1/2. Agreed?
Agreed.
Okay. So then from here, with your calculators, you guys can do this. You should get an approximation of 0.6935150. We all right?
Yeah.
Okay. Now, one of the things I want to show you, so this was for the Simpsons rule for 10 subdivisions. I wanted to show you so you guys can get the comparison of all of them. The actual integral is at 0.693147. Simpsons is 0.693150. That's pretty good, right? Trapezoid is 0.693771. And then midpoint was 0.692835. And you can see from here, right, that Simpsons is clearly better than the other two. Right?
Yeah.
Yes.
All right. Now, I showed you how to find error for the trapezoid. I showed you how to find error for midpoint. Now I'm going to show you how to find error for Simpson. And here it is. Now here it's it's much more complicated, right? Well, I mean, the numbers end up being similar, simple, but it's k times a quantity b minus a to the 5th power divided by 180 n to the 4th. Oh, one thing I wanted to go back to this guy that I didn't. No, I'll show it to you here. I'm gonna get to the n number in this example, which is the big deal. So in this, we're gonna find what the error is to have the same accuracy as the others. So do you remember with trapezoid in the notes, how many n's did I need to be able to have an accuracy of 0.0001? Do you guys recall?
Wasn't it 5?
No. When I was going to get the error.
Oh,
Right,
the error.
to get the error. So here they are. So for trapezoid, it was 41.
Yeah.
For midpoint, it was 29. So you can see 41 and 29, right? So is that a lot of work if we're going to do it by hand?
Yes.
It becomes kind of tedious, right? So with the Simpsons rule, let's see if it's going to be better. Okay? So one thing, though, here that we need to notice is with Simpsons rule, now we have to take the fourth derivative. You guys see that? That symbol means to take the fourth derivative. So Calc 1 becomes a big deal, right? Because you should be able to fly and do these like I'm doing them right now. And get to the fourth derivative like that. So that means we need to make sure that we have our derivative practice down, right?
Right.
But these aren't too bad, so I think you guys will be able to do it. And so to go get my k, my k is going to be that derivative, which is 24 over x to the fifth. Has to be less than or equal to the 24. But I know my x on the lower bound side, that gap is 1. So my k is going to be 24. My a is 1. My b is 2. We okay with that?
Yes.
All right. So then from here, applying the rules, I'm going to get 24, 2 minus 1 to the fifth over 180 n to the fourth should be strictly less than that 0.0001. Okay? Cleaning that up, I'm going to get 24 over 180 times 0.0001 should be less than n to the fourth. So my n is going to be 1 over the fourth root of 0.00075. And I'm going to get 6.04. Right? So if it's 6.04, what should my n be?
6.
7.
I think 6. Was it?
I would think
has to be
6.
higher.
Someone said 7. Someone said 6. Remember, I said if it's bigger than the number at all, we have to go up. Correct?
So 7.
Correct.
7 then.
Everyone wants to say 7, but I highlighted something when I talked about Simpsons Rule. And this is where you'll make your mistakes. What does n have to be?
An even number.
So if it can't be 6, it's going to have to be
8.
It is 8. It's overkill, but it's 8. Because we need to remember that n must be even. But look at the work. Trap was 41. Midpoint was 29. And Simpson is 8. We want to be efficient, right? And so to be efficient, now we're using some calculus to help us get to good curve approximations. Does that make sense?
Yes.
Okay. All right, I'm going to stop recording right here so I can have this video safely protected. And then I'll answer some homework questions or whatever you might have for me, okay?